All right, so let's do some more examples of, of matrix multiplication. So let's do something like, let's take I don't know, Let's take a 3 by 4 matrix and multiply that by a 4 by 2 matrix, same number of columns and rows, and so we will end up with a 3 by 2 matrix. I hope I don't run out of space here. Okay, let's see, 3 by 4. So 3 by 4 is going to be 3 rows, something like that, 4 columns. Again, I'm going to stick with smallish numbers. Let's go for 1, 0, 2, 0, 0, -1, 3, 2, 4, 0, 0, 1. That's my 3 by 4. I'm going to multiply that. I mean, again, I generally don't have to draw the multiplication symbol, but I just put it there for kicks. And my 4 by 2 is going to be 1, 0, -1, 2, 3, 5, 0, 1. Okay. So to sort of illustrate what I was saying at the end of the last video, the way that I like to sort of imagine doing this is I'll draw my finger across this top row. I'm looking for the 1, 1 entry. So that means the first row and the first column. So I'll draw my left finger across here and my right finger across here. And that tells me that I take 1 times 1 plus 0 times 0 plus 2 times -1, so that's -2, plus 0 times 2, so that's plus 0. Okay, then to get my second column, now to get the entry right here, the first row, second column, I'll draw my finger across the first row and down the second column. So 1 times 3 gives me 3, 0 times 5 gives me plus 0, 2 times 0 gives me another plus 0, and 0 times 1 gives me another plus 0. Okay? Now, for the second row here, I'll use the second row. First column gives me 0 times 1 is 0, -1 times 0 gives me another plus 0, 3 times -1 gives me -3, and 2 times 2 gives me plus 4. Now to get the second row, second column, look at the second row and the second column. 0 times 3 gives me 0, -1 times 5 gives me -5, 3 times 0 gives me plus 0, and 2 times 1 gives me plus 2. Then finally, to get the third row, I've got to get the third row down here. To get the first column, I use the first column here, so 4 times 1 gives me 4, 0 times 0 gives me plus 0, 0 times -1 gives me plus another 0, 1 times 2 gives me plus 2, and then to get the last guy, last row, last column, 4 times 3 gives me 12, 0 times 5 gives me plus 0, 0 times 0 gives me plus another 0, and 1 times 1 gives me plus 1. And what is the result here? I end up with 1 minus 2, that's -1, 3 plus a bunch of zeros, that's 3, -3 plus 4, which is 1, -5 plus 2, which is -3, 4 plus 2, which is 6, and 12 plus 1, which is 13. And so that will be my final answer here. Again, I get 3 rows and 2 columns because this had 3 rows, this had 2 columns. But I was able to multiply them because the number of columns of the first matrix was the number of rows of the second matrix. Okay. Let's see some weird things about multiplying matrices. There's some things that we have to worry about. First of all, multiplying matrices is not commutative, so not commutative in general. What is commutative? What this means is that if I take two matrices x and y, in general, x times y is not equal to y times x. And this is easy to see in some cases. For example, a 3 by 2 matrix, let's say that, let's say I have a matrix X, which is 3 by 2, and Y, which is 2 by 3. Then I can multiply them in either direction, but X times Y is 3 by 3, and Y times X would be 2 by 2. So most certainly these two guys are not equal to each other. X times Y is a 3 by 2 times a 2 by 3, so I get 3 by 3. Y times X is 2 by 3 times 3 by 2, so I get 2 by 2. But then you might say, okay, what happens if I look at two matrices which happen to actually, say, give the same size? So let's look at, say, some 2 by 2 matrices. Let's look at, I don't know, 1, 1, 0, 1, and let's let this be X, and let's let Y be 0, negative 1, 1, 0. What we get is this. If I take X times Y, what do I get? My first entry is I go across X and down Y, so 1 times 0 is 0, 1 times 1 is plus 1. My first row, second column is 1 times negative 1 is negative 1, 1 times 0 is 0. My second row times my first column is 0 times 0 is 0, and 1 times 1 is 1. And my second row times my second column is 0 times negative 1 is 0, 1 times 0 is 0. So what do I get? I get the matrix 1, negative 1, 1, 0. Okay, what if I take Y times X? What do I get here? Well, now I'm using the rows of Y and the columns of X. So the first row of Y is 0, negative 1, and the first column of X is 1, 0. So 0 times 1 gives me 0. Negative 1 times 0 gives me 0. My first row of Y times my second row of X gives me 0 times 1 is 0. Minus 1 times 1 is minus 1. On the bottom, I get my second row in Y is 1, 0. My first column in X is 1, 0, so 1 times 1 is 1. 0 times 0 is 0. And my bottom row in my right column give me 1 times 1 is 1. And 0 times 1 is 0. So I end up with 0, negative 1, 1, 1. They look similar to each other, but they're different, because this has a 1 in the upper left, this has a 0, this has a 0 in the lower right, this has a 1 in the lower right. These other two entries are the same, but that's, sort of a weird thing right there. Okay, what else? We can have two non-zero matrices can multiply to 0. So for example, if I took the matrix 0, 1, 0, 1 and multiplied it against itself, 0, 1, 0, 1, 0, 0, what do I end up with? 0 times 0 plus 1 times 0 is 0. 0 times 1 plus 1 times 0 is 0. And the bottom row here is 0, so 0, 0, 0, 0, 0 gives me 0, 0, 0, 0, 0 gives me 0. So this gives me a matrix whose product is equal to 0, even though these two guys are not 0. So that is another weird thing about matrix multiplication. Now there's some special matrices that I forget if the book actually goes into it in this case, but for any number m, we have an m by m identity matrix. And what it looks like is this. We generally denote it by I, and it has ones on the main diagonal, and it has zeros everywhere else. So what do I mean by this? Well, we have the 2 by 2 identity matrix, which looks like 1, 0, 0, 1. We've got the 3 by 3 identity matrix, which looks like 1, 0, 0, 0, 1, 0, 0, 0, 1, and etc. And the fact here is that so long as the product makes sense, x times I is equal to x, and I times x is equal to x for any matrix. And let me just do an example of that now. I'm going to pick an eraser, erase. Okay, and go back to here. So let me take the matrix, the 2 by 2 times a 2 by 3. So 1, 0, 0, 1 times a 2 by 3, 2 rows and 3 columns, 1, 2, 3, 0, 1, 4. What do I get here? 1 times 1 plus 0 times 0 gives me 1. 1 times 2 plus 0 times 1 gives me 2 plus 0, so that's 2. 1 times 3 plus 0 times 4, that's 3 plus 0, that's 3. On the bottom I get 0, 0 times 1, which is 0, plus 1 times 0, which is 0. Here, right here I get 0 times 2 is 0, plus 1 times 1 is 1. And over here I get 0 times 3 is 0, and 1 times 4 is 4, so I get that. Okay. As an exercise, you can check that going the other way. I can't multiply on the right by the 2 by 2 identity matrix, but as an exercise, why don't you check that multiplying on the right by the 3 by 3 identity matrix also does the same thing. So do yourself. Okay. Let's see if there's anything else I wanted to say. The one question that this raises for us, and this is just philosophical, is division. We have an identity matrix, which kind of plays the role of the number 1, because when I multiply against something, I get it back. The question is, can I then divide? And division is much harder, and it's going to turn out that it only makes sense for certain square matrices. In fact, it makes sense for most square matrices, but they have to be square. There's no way that you could have non-square matrices where it really makes sense to divide. But this is the topic of section 4.5. Okay, I think I'm going to put up a video with some applications actually of both section 4.3 and section 4.4, so I'll do this soon. Okay.